Welcome to our explainer. Today, we're diving deep into a really powerful tool called Sigma Metrics. It's what helps make sure the lab results your doctor relies on are as accurate and safe as they possibly can be.
So let's start with a really big question. Every single day, clinical labs are churning out millions of patient results that directly impact people's health. So how on earth do they manage the quality and risk across hundreds of different tests when each one behaves a little differently? It's a huge operational challenge.
For a long time, the approach was pretty much one size fits all. A super stable test got the same quality control as a much more, let's say, temperamental one. This was not only inefficient, it could actually be pretty risky. But now, the modern approach is so much smarter. It's a risk-based strategy, and the engine that makes it all work is Sigma Metrics. This lets labs focus their energy where it's needed most, making sure things are safe without wasting a ton of resources.
The Sigma metric. Think of it as this beautiful all-in-one score. It combines how accurate a test is, how close it gets to the true value, with how precise it is, meaning how consistent it is over time. But here's the kicker. The most crucial part is what this score does. It determines the entire quality control strategy for that test. It is the master key.
First up, we have total allowable error, or TAA for short. The easiest way to think about this is as a test's total error budget. It's the absolute maximum amount of error a result can have before it's no longer clinically useful, before it could actually mislead a doctor. And this budget isn't just some random number. It's set by official sources that have to be documented, like regulatory agencies, or from data on how much a test naturally varies in the human body.
Okay, ingredient number 2 is bias. This is the test's consistent, systematic error. It's like a bathroom scale that always tells you you're 2 pounds heavier than you really are. That's bias. It's a predictable error that's always pushing results in one direction, away from the true value. And to measure it right, you really need to use special reference materials that are commutable, which is just a fancy way of saying they act just like real patient samples.
And our third and final ingredient is imprecision. Now, this is the random, unpredictable scatter you see when you measure the exact same sample over and over again. So if your scale gives you slightly different readings each time, 150.1, then 149.8, then 150.3, that wobble, that fluctuation, that's imprecision. We measure it using standard deviation, or SD, and the coefficient of variation, or CV. It's also super important to document if you're measuring it over a short or long period of time, because that can change things. So this is a great way to see how it all fits together. You start with your total error budget, the TEA. Then, that budget gets eaten up by 2 things, the consistent error, your bias, and the random error, your imprecision. And really, the Sigma score is just a brilliant way to measure the relationship between all 3. So how do we actually combine this error budget with those 2 types of error? Well, that brings us right to the Sigma formula, which elegantly turns these 3 separate ingredients into one single powerful number. And here it is, in both its percentage and its absolute form. Now, I know, it might look a little intimidating at first glance, but the logic behind it is actually super intuitive. You can see in both versions, you take your total error budget, you subtract out the bias, and then you divide whatever is left by your imprecision. Let's dig into what that really means.
This really just says it all. This is the core question the formula is asking. That top part of the fraction, TEA minus bias, that's your remaining error budget after you account for that consistent error. The formula then asks, okay, how many times can our random error, our wobble, fit into that remaining space? It's basically measuring your safety margin. The higher the number, the bigger your margin for error is.
Okay, now this is huge. This is the single most important rule, and it's the most common mistake people make. You have to be consistent with your units. All 3 of your inputs, TE, bias, and imprecision, they either all have to be percentages or they all have to be in the absolute units of the test. If you mix and match, your final score will be completely wrong. It's that simple.
Our first case is a glucose test. Here are the starting numbers we're working with. The total allowable error, which is set by CLIA, is 10%. The target value for our quality control material is 100, but our lab is consistently getting a result of 105, and our random variation, the standard deviation, is 2.1.
All right, now let's see how we put these inputs to work. First, we need to calculate our bias as a percentage. The difference between our lab's mean, 105, and the target, 100, is 5. And 5 is, of course, 5% of 100. Simple enough. Next, we calculate our imprecision as a percentage, which we call the CV%. We just divide our standard deviation, 2.1, by our observed mean of 105, which gives us 2%. Finally, we plug it all into the formula. We take our 10% TEA, subtract the 5% bias, which leaves us with 5%. We divide that by our 2% CV, and we get a sigma score of 2.5.
Very top of that ladder, you've got world-class performance. These are the rock stars, the tests with a sigma score of 6 or higher. You can think of these as the luxury sedans of the lab. They're incredibly robust, super precise, and the chance of them making a mistake is vanishingly small. Now, because these tests are so darn reliable, the quality control strategy can be pretty relaxed. Labs use a very simple rule, often called a 1-3S rule, that's just designed to catch huge, obvious errors. And get this, they only need to run this check every 100 to maybe even 1,000 patient samples. If an error does pop up, the first step is usually just to rerun it, because a real problem is just that unlikely. And this is a perfect real-world example. You have a highly automated chemistry test with a sigma of 7, firmly in that world-class zone. It might only get a single quality check after running 500 patient samples. That's the kind of confidence we're talking about. Okay, let's take one step down the ladder. Next up, we have tests with good performance. Their sigma score is somewhere between 4 and 6. Now, these tests are still very reliable, totally fine for clinical use, but they just require a little more vigilance. So right away, you see the safety net gets tighter. In addition to that first simple rule, labs add a second one, like a 2-2 cis rule, which is designed to catch more subtle problems, like when 2 checks in a row are just a little bit off. They check more often too, every 50 to 200 samples, and if something goes wrong, the investigation gets a little more serious. A hormone test with a sigma of 4.5 is a great example here. It uses that 2-rule combo and gets checked every 100 patients. You can see that direct link, right? The sigma score drops a bit and the monitoring immediately ramps up to match. Now things are starting to get more serious. We're in the marginal performance zone, with a sigma between 3 and 4. These tests are still considered acceptable, but they are walking a very fine line. A small change in the lab environment could easily push them into an unsafe state. So here, the QC plan becomes much more robust. Labs deploy a full set of complex rules, the whole shebang, looking for all sorts of subtle patterns. They're checking very frequently now, sometimes after as few as 20 patient samples. And if any rule is broken, the action is immediate and serious. Patient results get put on hold. An immunoassay with a sigma of 3.2 is a perfect case study. It gets the full multi-rule treatment with duplicate checks running every 20 to 40 patients. The intensity of monitoring has just increased dramatically from where we started. And now we've reached the bottom of the ladder, high-risk performance. Any test with a sigma score below 3 is just not considered reliable enough for routine clinical use. It poses a significant risk of producing wrong results, unless there's extreme oversight. For these tests, the strategy is all about maximum containment. Labs use every rule in the book to detect the absolute smallest deviation. They check constantly, maybe every 5 to 20 samples, and if an error is flagged, the action is severe. They stop reporting patient results entirely and launch a full-scale investigation to find the root cause. This example just brings it all home. A test with a sigma of 2.1 is under a microscope on every single run. Holding patient results isn't just a possibility, it's the standard procedure on any failure. The goal here isn't just managing risk, but ultimately, it's about improving or replacing this test altogether. And it really comes down to 3 core ideas. First, the potential risk to a patient always comes first. It's the ultimate guide. Second, a quality control plan is a living document. It's dynamic, not something you just set and forget. And third, for less reliable tests, running more checks or replicates just builds more confidence in the final decision. And this quote right here highlights the most important principle of all. It doesn't matter if a test has a good sigma score on paper. If that test is used to make a life or death decision, like for a heart attack, the lab will always choose the strictest rules. Patient safety always overrides the raw number. Well, they use a pretty simple 5-step process. Step 1, you calculate the sigma score. Step 2, you map that score to the strategy tables we just walked through. Step 3, you make that plan even stricter for any of those marginal or high-risk tests. Step 4, you follow a clear protocol whenever a rule is broken. And finally, Step 5, after you fix a problem, you reevaluate and document everything to prove the fix actually worked. It's a systematic loop of measurement, action, and verification.